Hello and welcome to the first lectures on MOS inverters. As I mentioned in my first lecture that it will be we shall discuss various aspects in a using a bottom up approach. So, in the last 4 lectures I have discussed various aspects of MOS transistors starting from fabrication, characteristics, and then various issues related to MOS transistors and MOS transistor as a switch. Now, we shall discuss about MOS inverters, and here is the agenda of today's lecture. After giving a brief introduction about what do we really mean by inverter, we shall consider a generic structure of a MOS inverter, how we can realize MOS inverter. Then discuss two important characteristics, one is your transfer characteristics and another important feature is noise margin. And then we shall discuss about the realization of MOS inverters using different approaches. Number 1 is passive resistor as pull up device, NMOS depletion mode transistor as pull up device, NMOS enhancement mode transistor as pull up device, and PMOS transistor as pull up device. Okay. As you know, the inverter forms the basic building block of gate based digital circuits. You must notice the word gate based. Actually, MOS circuits can be of two types. Number 1 is gate based. In gate based circuit, what you do? You apply your signal to the input of to the gate and take the output from the source, usually I mean drain, usually the source is grounded. This is one. And another approach that I have already discussed when we considered MOS transistor as a switch, there we have seen that signal that you are applying, we are not applying it to the gate, we are applying to the source or the drain, and gate is being used as a control circuit. I mean with the help of gate we control it. Another is gate based and second one is switch based. In this case we usually apply as you have seen, here it is your input, here also it is V in, and you take the output from here, and here this is control circuit, we apply the control signal here to control the resistance of this transistor and we take the output from here. So, this is your switch based logic, another is gate based logic. And later on we shall discuss about the use of MOS transistors based on switch based logic. For the time being we shall focus on the realization of MOS inverter, which is essentially based on applying input to the gate, as you can see here. Now, how you can realize a MOS transistor inverter? An inverter can be realized with the source as an source of an NMOS enhancement mode transistor, and the source is connected to the ground and the drain connected to the positive supply rail VDD through a pull up device. So, the general structure will be somewhat like this. You will have what is known as pull up device, and we will also have a pull down device, which is essentially a NMOS transistor, and here we shall apply input to the gate of the NMOS transistor and we shall take the output from the drain of the NMOS transistor. This is your V output. Now, in this particular structure, this NMOS transistor is called as pull down device, and the upper one is called pull up device, and as we shall see, the pull up device can be realized in a number of ways. That is why I have not written any I mean I have not drawn anything, any transistor or anything, but we shall see what are the different alternatives available. You may be asking why you are giving the name pull up device, pull down device. The reason for that is, as we shall see, it will be associated with a capacitance at the output. That means, with the help of pull up device you pull the voltage up to the VDD level. On the other hand, with the help of, that means when the pull up device is on, then this capacitor charges through this pull up device, rather the voltage is raised to VDD level through this pull up device. And obviously, as you know, the MOS transistors are voltage control devices, the pull up devices also will be device will be a voltage control device, or it may be passive transistor, as we shall see later. And this is the pull down device, with the help of which whenever this NMOS transistor is on, you will pull the voltage down to ground level, because this is ground. So, this is the basic structure of a CMOS inverter. We have a pull up device, we have a pull down device, and some capacitance is associated to the output of the inverter. And as I have mentioned, the input voltage is applied to the gate of the NMOS transistor with respect to the ground, and output is taken from the drain. And as I have told, NMOS transistor is called pull down device, and the other device which is connected to the VDD is called the pull up device. Okay. Now, whenever you draw the basic structure of a circuit, for irrespective of the realization, usually we represent an inverter with the help of this logical symbol. This is the symbol of an inverter. You are familiar with it, irrespective of the way it is realized. And how do you represent its characteristics? You can represent the characteristic of a inverter with the help of a truth table, because it is a digital circuit, and truth table is the way by which is the manner by which you can represent the functionality of the inverter. So, truth table. So, in the truth table there will be two columns, one for V input, another for V output, and you have got two possible inputs that you can apply. One is your 0, another is 1, and when you apply 0, since this is an inverter, it inverts the input. So, output will be 1, and when the input is 1, output will be 0. So, this is a very simple circuit, but it is the most fundamental building block of digital circuits. So, with the help of this truth table, you can represent the function of a MOS inverter or any kind of inverter, because it is not only the MOS inverter, you can represent the function of any inverter. Okay. Now, we shall consider a characteristic, important characteristic, which is known as transfer characteristic. So, transfer characteristic of a inverter, let me draw it here. This is the transfer characteristic. Transfer characteristic. So, the transfer characteristic is essentially represents how exactly the output changes as you change the input. So, this is your input and this is your output. So, how the input gets transferred, I mean input changes the output, and that is the represented with the help of the transfer characteristic. Ideally, an inverter will have a transfer characteristic like this. As you change the input from 0 to VDD, output will switch from 1 to 0. That means, for input, whenever V in is in the range of 0 to VDD by 2, V output is equal to 1. As you can see, V output is 1 or VDD, that is your VDD. On the other hand, when the input is V in is V is in the is greater than V is in greater than your is greater than VDD by 2, this is your VDD by 2. So, this is in the range of VDD and VDD by 2. Then V out is 0 or ground. So, this is the ideal characteristic of an inverter, and as you can see here, the as you this input is abruptly changing at the middle, that means whenever the input voltage is VDD by 2, and this is usually is known as VT. VT or inversion threshold voltage, usually it occurs whenever V in is equal to V out. That means, when V in is equal to VDD by 2, V out is also VDD by 2, that is the main feature of this VT in the ideal situation. So, VT is the this is the inverter threshold voltage. We have seen a MOS transistor has got a threshold voltage, but here we are defining a threshold voltage of the inverter. So, VT is the inverter threshold voltage, and this is occurring at VDD, ideally it should occur at VDD by 2. But unfortunately, this ideal characteristic cannot be realized by any real life inverter circuit, including MOS transistor, realization by using MOS transistors. So, ideal realistic situation will be different from the ideal characteristics of the inverter. So, how it will look like? So, as you can see here, the actual characteristic is somewhat different from the ideal characteristic. We can redraw it here for your convenience. You can see here, again this is your V in and this is your V out, and input is changing from 0 to VDD, and initially when the input is 0, output may be equal to VDD or little less than VDD. Why? We shall see later whenever we go for actual representation. And then it will not really change abruptly, it will follow a kind of smooth curve, and it will be somewhat like this. That means, this need not be, say, suppose this is VDD. So, it may be little less than VDD. Similarly, the low level may not be exactly 0, this is actually somewhat less than little more than 0. So, it is called the VOL, output level low, and this is called the VOH, output level, high level output, which is represented by this here. Actually, this VOH and OL is also defined in some other way. You can draw a curve, draw a tangent to this curve, where V output dV output dV input is equal to -1. So, where the slope is -1, this point represent that, this point also represent that, where the slope is -1, and actually this VOH is represented by this point, where it is this transition is taking place from 1 to 0, and it is defined by this line, where dV out dV in is equal to -1. Similarly, here this point where dV out by dV in is equal to -1. So, this region is the transition region, this is represented by the VOL. So, VOH and VOL, as you can see, need not be VDD or 0 in real life or in actual situation. Similarly, we have already discussed about that inversion threshold voltage in the inverter threshold voltage. So, inverter threshold voltage also need not be equal to VDD by 2. This point where V in, this is actually a line where which has been drawn where V in is equal to V output out. So, this is the point where it is crossing, and this particular voltage need not be equal to VDD by 2, but this is represented as VT. So, VT in ideal situation is VDD by 2, but in practice it need not be VDD by 2, it can be less than VDD by 2 or more than VDD by 2. We shall see on what parameters it will depend. Okay. Now, after discussing the transfer characteristic, let us discuss about another very important characteristic, that is your noise margin. Noise margin. What do you really mean by noise margin? What is the physical significance of this term noise margin? Noise margin actually characterizes the behavior of the device in presence of noise, whether the device will function correctly, accurately in presence of noise or not. That is actually decided by the noise margin factor. For example, if we look at this particular ideal characteristic, there you can see if the input voltage is in the range 0 to VDD by 2, output is high. That means, input can change in this range. So, in this range the input can change, still the output will be accurate. That means, on top of 0 volt, if there is noise, and as long as the noise level does not exceed VDD by 2, you will get correct output. So, that is why this is called noise margin NH low, that is 0 to VDD. Similarly, you can see here, as long as the input voltage is in the range VDD by 2, now ideally it should be VDD. That means, in case of digital circuits we have seen that for an inverter to get 0 output, your input is VDD high, but there may be noise because of the some transition that is occurring in some other circuit that will change the ground voltage, there will be noise because of industrial and various other reasons. And as a consequence, you can see here the voltage may vary may be little less than VDD, but as long as the voltage input voltage is in this range VDD by 2 to VDD, output will be correct. So, that is why the noise margin noise margin high. So, noise margin high you can see is also in this range. That means, for an ideal device, ideal inverter, noise margin low is equal to VDD by 2, you can see 0 to VDD by 2. So, it is VDD by 2, and in case of noise margin high, in the high level also it is VDD by 2. That is the ideal situation. But what about the practical situation in this case? Will it be like this? To discuss about that, let us consider a situation where you are applying the output of an inverter to another inverter. Obviously, in between you have got some kind of interconnect. Interconnect will have some resistance, and here the output will change. Output of one inverter is being applied to the input of another inverter. So, in this case we can represent the voltage levels. For example, say this is the input to the next level here, and here is the output of the first inverter and this is the input of the second inverter. Now, using this diagram we can see that the this is the VDD, let us assume this is the VDD, this is VDD, but we know that output high, we have already seen that output high as we can see here need not be really VDD. So, it may be little less than VDD as you can see in a actual inverter circuit. So, we can say that this is the VOH. So, VOH that is being generated, output high that is being generated by this inverter and which is applied to this next stage of inverter. And this next stage of inverter is receiving input, and how long it will function properly? As long as you can see here, as long as the input is in this range, it will continue to function. So, this line where this is touching, it is called VIL. That means, as long as the input, low level input is in this range 0 to VIL, output will be VOH. So, this VIL, as long as this is the situation, it will be like this. And similarly, you can see here, as long as the input is above this point VIH. So, VIH, as long as this is input high, output will be low. It is above this VIH level, output will be high. That means, input level, if it is more than VIH, then output will be 0. So, here you can represent that, say this is your VOH and here this is your VIH, this is being applied to this input. So, VOH is generated by this stage and VIH, which is required considered to be an input for high level, which will produce a low level at the output, maybe is little lower than that. As you can see here, VOH is a little lower than this. Similarly, this VOL, let us assume this is your VOL that is being generated by this. VOL is generated, VOL is here, VOL is generated. Whenever the output is low, it will generate a voltage like this. But how long the output will be, it will be considered as a low level? Up to VIL level. So, up to VIL level, VIL is somewhere here. So, this is your VIL. So, these are the inputs required for this stage and these are the outputs generated by this stage, and this is essentially the noise margin high and this is the noise margin low. Now, let us write down various equations for NMH, NML and so on. So, when you are getting logic 0 input, remains in what range? 0 less than equal to V in less than equal to VIL. This is the logic level output possible, we have seen, and logic 0 output is VIH, VIN and VDD in this range, VIH to this range. As long as it is in this range, this is the logic level output that is being produced. Similarly, logic 1 input is in the range of VIH, Vin less than equal to VDD. This is your logic 1 input in this range. This is VIH is in this range. So, this is the range VIH, and logic 1 output is in the range of VOH, VO less than equal to VDD. So, you can see these are the input output characteristics. Now, so what is your NML, noise margin low, that is equal to VIL minus VOL. Similarly, NMH, this is the range, NMH is equal to VOH minus VIH. So, this is how we can define the noise margin level low and noise margin level high. You may notice that this noise margin level low and noise margin level high will not be equal to VDD by 2, as we got it in case of ideal situation. In both the cases it will be less than VDD by 2, and as a consequence in actual implementation the noise margin that you will be getting may be less than VDD by 2, and how less, that will actually decide the robustness of the circuit, how it will behave in presence of noise, that will be decided by this noise margin. Now, let us focus on, after discussing in detail the operation, or the important characteristics of an inverter, ideal and actual, let us see how actually you can realize an inverter. So, first way, the first implementation technique is by using a passive resistor as pull-up device. So, what you are doing in this particular case, you are you are using a passive resistor RL as pull-up device, and you are connecting the NMOS transistor as pull down device, and so this is your VDD, this is ground, and here is your V input, and here is your V output. Now, in this particular situation, how the output will change as you change the input? How do you find out that? You will be interested in characterizing the feature, characterizing the operation of a MOS inverter implemented by this technique. What you can do for that purpose, you can plot a curve where x axis will be VDS, and now the y axis is say IDS, and you already know the characteristic of a NMOS transistor. So, it will be like this. For different gate voltages you will get curve like this, and gate voltage will vary depending on the input voltage change. Here V in is equal to VGS, gate to source voltage. What about how the output will change? To know about how the output will change, you will draw a line which is known as load line, which essentially represents the resistance of this resistor, load resistor that you have connected. Now the operation of the device can be characterized. You can see the input will change from 0 to VDD, say this is 0, let us assume this is VDD. As the input is changed from 0 to VDD, how the output changes. So, when let us start with when the input is VDD. When the input is VDD, what is the output? What output will be getting? 0, because when the input is sorry, when input is, this is your, oh I have not drawn, this is not the input output characteristic. As you can see, when the to do that we have to draw the transfer characteristic, but here what you are doing, you are applying the input here. So, input is changing from 0 to VDD. So, when the input is 0, what will be the output? This transistor will be off. So, you will get output VDD. So, this point A corresponds to V in is equal to 0 and V out is equal to VDD. Then let us consider point V. What does it represent? This is A. So, point V represents a input when it is where it is where the input is higher than the threshold voltage, because the NMOS transistor has started conducting. So, V in is greater than V T n. So, input voltage is greater than V T n. Obviously, this point, all of them are representing that. So, in this case your V out will be equal to will be somewhere. So, it will be in the range of 0 to VO VDD, somewhere in between. Now, let us consider point C. This is point C. Point C represents when the input is VDD, where when you have applied an input VDD, V in is equal to VDD. So, it is in this point B is V in is greater than VTN, but less than VDD, that I have not written. So, in this case V out is equal to VOL. This is actually VOL. I mean this will correspond to this point. This point will represent that. Now, we can see how the operation of the MOS transistor is changing. So, in point A corresponds to when the MOS transistor is cut off, operating in the cut off region. Point A represents when the MOS transistor is off. So, it is operating in the cut off region. What about point B? Point B, you can say that MOS transistor is in saturation, NMOS in saturation. In point C, you note that it is no longer in the saturation region, it is in NMOS in linear region, linear or weak inversion region. So, as the input changes from 0 to VDD, the transistor switches from cut off to saturation to linear region. So, we can draw the transfer characteristic as well. So, let us draw the transfer characteristic here. In transfer characteristic, what do you plot? How the output changes with input. So, V in and V out. So, we have seen when the input voltage is 0, then we got output VDD, because this transistor was off. So, you will get all the voltage will be dropped across this resistor. So, you will get a voltage which is equal to VDD. Then as the input is increased, it switches, but you can see your output voltage, whenever the input is VDD, output voltage is VOL, which is no longer 0. That means, we can see here VOL is greater than 0 volt. That means, in this what we are observing from this realization, that whenever a passive resistor is used as pull-up device, you are getting a strong output, high level output, but weak low level output. By that, what do you mean? By strong high level output, we mean that whenever output is supposed to be high, we are getting full high level voltage, that is your VDD. On the other hand, when the output is supposed to be low level, that is 0, we are not getting 0, but little higher than 0. So, it is a, we consider it as a weak low level output. Now, you may be asking on what factor this low level output will depend. So, on what factor VOL will depend. So, VOL, how do you find out the value of VOL? So, VOL is equal to VDD into RC, where RC is the channel resistance of this transistor. That means, when this is operating in this range at this point linear range, it will have some finite resistance. So, that since it is a voltage control device, it will have some resistance, voltage control resistor, it will have some finite resistance. So, voltage will be developed across it, and that voltage that voltage is the output voltage, and here this RL and RC together is forming a voltage divider. So, they are in series. So, what is the voltage across the RC? It is equal to VDD into RC by RC plus RL, simple Ohm's law. Question is, this low level output, will you consider this low level output acceptable? How low it is? If it is not 0, obviously, how far away it is from 0, how much higher it is from 0, that you have to know, and up to which point it will operate correctly. We know that the output of an the output of this supposed to be an inverter will be applied to another stage of an inverter. So, here you will be applying VOL. You have to see whether this next stage will accept this low level as a real low level, acceptable low level voltage. What is the characteristics of a low level voltage? That voltage should be such that it will not make the next stage transistor on, then the output of the next stage will be high, is not it. So, what is the requirement? Requirement is this VOL should be less than VTN, supposed to be, because this is also being applied to another transistor, and obviously, the output of the next stage will be high provided the input is less than the threshold voltage. So, VOL should be less than VTN, that is the requirement to be satisfied for the correct operation of the inverter. So far as the high level is concerned, there is no problem, we are getting VDD, there is problem with low level output. So, low level output has to be less than VTN. Normally, this threshold voltage VTN has some nominal value, let it be 0.2 VDD. Typically the threshold voltage has some relationship with the supply voltage, that is equal to 0.2 VDD. That means, if we substitute it here in this expression, that means this is equal to 0.2 VDD. Then what condition it requires? What is the outcome? That means, VOL in place of VOL we shall be substituting this 0.2 VDD. That means, VDD into RC by RC plus RL should be less than VDD into 0.2 VDD. So, if you solve this equation, what will you get? You will get that your RL, you see VDD will cancel out. So, this side will be equal to 0.2 RC plus RL. So, that means, RC should be less than 0.2 RC plus RL, or RL should be greater than 4 RC. That means, the resistance of this load resistance, the passive resistor that you have put, has to be at least 4 times the resistance of this channel resistance RC. So, that is a very stringent requirement. Without that, it will not behave as, it will not operate as an inverter. It will not be, its operation as an inverter is not acceptable. Now, based on this, what are the limitations and advantages of a MOS inverter realized using passive resistor is let us see disadvantages. First of all, it is unsuitable for VLSI fabrication. Why it is unsuitable for VLSI fabrication? Whenever you try to realize a passive resistor in VLSI, you can use two possible approaches. One is diffusion based approach, that means you will create a diffusion region, isolated diffusion region, whose resistance has to be equal to 4 RC, and obviously it will require lots of area. Another alternative is you can use polysilicon without doping, undoped, and that can be used as a resistor. But unfortunately, whenever you use this second approach, its value cannot be accurately controlled because of wide process parameter variation of VLSI technology. As a consequence, this realization of MOS inverter using passive resistor as pull-up device is not feasible. And I have already mentioned, it will occupy large chip area, either way, whether it is a diffusion based realization or realization by using that polysilicon, undoped polysilicon based realization. Secondly, it provides you weak low level, as we have already seen. The output level is not really 0. So, here you are getting a voltage which is higher than 0. So, we can say the output is weak. Then third factor, which is very important, asymmetric switching characteristic. What do you really mean by asymmetric switching characteristic? You see, we have seen, we shall see later on that operation of MOS circuits are essentially charging and discharging of capacitors. So, charging of discharging of capacitors, that means here you will be having some capacitor connected, and this capacitor has to be charged through this RL and discharged through RC. Since RL has to be 4 times RC, obviously this charging time will be at least 4 times that of the discharging time. So, charging and discharging times are not same, asymmetric. Obviously, on time and off time, or low to high level and high to low level transition times will be different, and which may not be acceptable in many situations. So, asymmetric switching characteristic. Fourth factor is large static power dissipation. What do you really mean by static power dissipation? Static power dissipation is when the input is not changing. Then what is the power dissipation? So, here as you can see, when this input voltage V in is equal to VDD, in this situation, that means input is high, then this transistor is on, and as a consequence there is the current will flow through this the RL RC network, and as a consequence there will be power dissipation. Obviously, the power dissipation will be dependent on RL and RC, and here also there is a kind of vicious circle. Vicious circle is this value of this resistance RL and also that of RC, if you want to reduce it to increase the speed of operation, then the power dissipation will be more. That means, higher the speed of operation, larger is the power dissipation. Obviously, it is not acceptable from low power applications, and particularly the static power dissipation is not acceptable in low power applications. So, these are because of these disadvantages, this realization of MOS inverters using passive resistor is not done, it is not feasible. So, what are the other alternatives? Next alternative is to use active pull-up device. So, active pull-up, active pull-up. So, whenever you say active pull-up, what do we really mean? We mean that we shall be using some active device. What kind of active device you will be using? Obviously, you will be using a MOS transistor, and we have 4 alternatives at our disposal. That pull-up device can be a NMOS enhancement type transistor, it can be a NMOS depletion type transistor, it can be a PMOS enhancement type transistor, or it can be a PMOS depletion type transistors. So, we have got 4 alternatives. Let us see which alternatives are good or acceptable and which can be used for the realization of MOS inverters. So, let us start with first alternative, that is your that is the case where we are using NMOS depletion type transistor as pull-up device. So, what we are doing here in this particular case, we shall be using a MOS transistor as pull-up device, and this is a depletion type NMOS transistor. So, when you are using an NMOS type depletion type transistor, what you can do? You can connect the gate to the source. Why so? Because since this is a depletion type transistors, if you connect this gate to the source, it will be always on. That means, it will offer a resistance. Always it will offer a resistance, because the gate is connected to the source and the transistor is on when gate is connected to the source. That is the basic feature of a NMOS depletion type transistor. Then you will be applying here input and you will be taking output from here, V output. So, what will be the characteristic of this device? How do you really obtain the characteristics of this device? What you can do? In the same way, you can plot VDS and IDS, and since this NMOS transistor can operate with different gate voltages, you have to draw several lines, several curves for the NMOS transistor, but there will be a single curve for the PMOS transistor. So, this is the curve for the PMOS transistor corresponding to VGS is equal to 0. Here gate is connected to the source. So, this corresponds to PMOS. So, PMOS is in linear region in this part and in saturation region in this part and linear region in this part. So, in this case, as the input changes from 0 to VDD, how the output will behave, or in what conditions this transistor will be, I mean this as well as that. So, when the input voltage V in is equal to 0 volt, then what will happen? This pull down device is off. So, V in is equal to 0 volt, this corresponds to point A. Point A, when pull down device off. What about the pull up device? Pull-up device is in linear region, you can see it is in the linear region. Pull-up, you have to not only tell it is on, you have to tell whether it is in saturation or in linear region. So, pull-up in linear region. When V in is equal to greater than V T n, threshold voltage of the NMOS transistor, then what will happen? It will move to maybe this point, say this point B, this is A, this is B. So, in this particular case what will happen? What is the operation of these transistors? Point B, pull up, pull down in which region? Linear region, in linear region, and pull up in pull up device is in no, here pull up device is also in linear region, pull down in linear, sorry, this is the pull up in saturation, sorry, pull down in saturation, it is not correct, in saturation here. So, it is in saturation and pull up in linear. Then when V in is equal to VDD, let us go to directly to this point, that is your point C. So, here what is the condition? Pull up is in linear and pull down in saturation. Pull down is in saturation because this part is linear. So, you can see here as the input voltage changes from 0 to VDD, the operation of these transistor changes. So, from the pull down device switches from off to linear, off to saturation, sorry, so pull down device switches from off to saturation. No, I have written wrongly. Pull up is this one linear, and pull down is linear. Sorry, it will be linear, and pull up, this is the pull up in saturation. I have written wrongly. Okay. Pull up in saturation, pull down in linear. Okay. So, based on this we can draw the transfer characteristic as well. So, transfer characteristic can also be drawn. What will be the transfer characteristic? Transfer characteristic will be, you can see here, when the input voltage is 0, what is the output you are getting? You are getting VDD, is not it? So, for this V in and here it is V out, transfer characteristic. So, it changes from 0 and then I mean VDD, output is VDD, but as you can see the low level output is not 0, just like your passive transistor. Here output is not 0. The reason for that is when input is VDD, then both the transistors are on. When the input is VDD, here it is VDD, both the transistors are on. Maybe pull up in saturation and pull down in linear, but this is the point, pull up in saturation, pull down in linear, and but both of them will be having some finite resistance. So, they will act a kind of voltage divider, and as a consequence what will happen, you will get a voltage which is not really 0, but little above 0. So, we are getting a voltage which is above 0, and obviously this is a non-ideal characteristic. So, what we can say about its the advantages and disadvantages. So, NMOS, whenever you are using NMOS depletion mode transistor as pull-up device, we find that the output is not ratioless. What do you mean by that? You see, if the output is dependent of the L by W of the ratio of the transistors, then we call it it is ratioed logic. What do you really mean by that? The resistance is dependent on the length, ratio of the length and width of the device, and whenever it is dependent on that, we call it ratioed logic. So, this is a ratioed logic, because output voltage at low level will be dependent on the resistance of the L and R. So, in this particular case, as we know, this resistance has to be 4 times that of this, that means length has to be, if it is 4 and width is 1, here it has to be 1:1. That means, length of this pull-up device has to be 4 times to of that of the pull-down device, and as a consequence this is a ratioed logic, and the output characteristics will not be symmetric, just like your transistor, I mean static resistor, and also there is static power dissipation when the output level is low. As we have seen, when the input is VDD, then output is low level and current flows through this path, because both the transistors are on and there is static power dissipation. And we have already seen that output level is strong, high level is strong and low level is weak. So, let us conclude today's lecture by summarizing what we have discussed today. We have introduced the basic concept of an inverter. We have introduced the characteristics of an ideal inverter in terms of noise margin and transfer characteristics. Then we have seen how you can realize a MOS inverter, and we have discussed 2 alternatives, one using passive resistor, another is by using a NMOS depletion mode transistor. So, in my next lecture I shall discuss about the other alternatives of realizing inverters, where we shall see how you can realize inverter by using NMOS depletion enhancement mode transistor as pull-up device, and also PMOS transistor as pull-up device. Thank you.